We have all noticed how the intensity of light changes with distance. We can see as the light source is moved further away from the wall, the light becomes less intense. We can see the same thing happening when we move the light away from this subject. This phenomenon is known as the inverse square law. The total amount of light energy that a star produces each second is termed its luminosity L, and would have units of joules per second. Since stars are far enough away to be point sources, the light is spread out equally in all directions, distributed over the surface area of a sphere whose radius r is the distance to the star. Since the surface area of a sphere is equal to 4 pi r squared, the intensity I of light that we see or measure with an instrument is given by intensity equals luminosity divided by the surface area of a sphere. We can explore this phenomenon with the following apparatus. We have a light source, a fiber optics cable that guides the light to a photometer that measures its intensity, and an interface to interpret the photometer's readings for the computer application. The bulb is sitting on a cart that reports its position to the computer, and we can physically move the light bulb, changing the distance between it and the dictator. We dim the lights and turn on our light bulb. We begin with the light bulb about 20 centimeters from the optical fiber. We start measuring the intensity of light and gradually increasing the distance between the light bulb and the optical fiber. When we carefully take intensity readings at a range of distances, we get the curve shown here, clearly displaying how light falls off as 1 over distance squared. Let's explore your understanding of the inverse square law with a peer instruction question. Compare the intensities of light through patches of concentric spheres centered on the sun. Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. Note that all the light energy that passes through the red square also passes through the 4 blue squares. Thus, the light intensity at a blue square must be 1/4 of that through the red square. The inverse square principle is of great importance in astronomy, as it is often difficult to obtain the distances to objects. There are several bins of astronomical objects known as standard candles, meaning that all members of each group have similar characteristics, and we have a pretty good idea of how luminous they are. Examples include pulsating stars like RR Lyrae stars and exploding stars like Type 1a supernova. Every Type 1a supernova has the same luminosity at its peak brightness. Astronomers measure the intensity of these objects, and since they know how luminous they are, they can then calculate their distances using the inverse square law. More teaching materials can be found at http://astro.unl.edu.